Okay, so let me start. So I have 5 lectures, and in principle, in the very end of the lecture, I hope to explain something about integral system and how to analyze and find the eigenvalue. And maybe I just formulate this distant goal and then move slowly in this direction, just to. So this old, or rather old problem, which I'm talking about, this is calling to find the eigenvalue of what people calling quantum Hamiltonians of Bldg type or Bldg equations. And by this, usually people have in a mind very concrete problem about Virasoro algebra. And this very concrete problem, and I think later I explain even something about Virasoro algebra, but let me just now formulate what the problem is. Well, if we have Virasoro algebra, so standard generators I belong to Z, and then such that G equal to G minus I plus G plus central term delta I plus G 0, and here is also standard expression like this. And here central element. So in the algebra we have this, we have central element also. This central element is here. Central element commutes with all I. And so this is the algebra, and surely almost all of us heard that this algebra is rather important in different kinds of business. But anyway, it has some Lie algebra, and it has representation. And representation, in principle, it has many different representations. But let me consider what is calling Fermat representation. Fermat representation, it means that it is a vector space depending on 2 numbers, which, so here let me put C capital. And here 2 numbers, one H and one C. Yes, and in this Fermat representation we have highest vector V, and we suppose that Li V is 0 if I is positive, L0 V is H times V, where H is this parameter. Central element acting by V has this small c, and times V. And standard name of this C is central charge. Well, and if it is Fermat representation, it means that you see that positive A killing highest weight vector, about H0 and C we know how they act on a highest weight vector. All other operators are freely give us new vector in a representation, so it means that representation itself with Fermat is looking by the following way. We have V, and usually we understand this is vector in a top. Then I can act by A minus 1 V, get new vector. Then I can act A minus 1 square V and A minus 2 V, A minus 1 Q n minus 1, n minus 2v, and n minus 3v, and so on. This is just a representation. I just counting vectors, and you see that here 1, 1, 2, 3, and so on. And from this picture, it is clear that on representation we have evident grading, and on each floor on this representation we have as many vectors as we have how many partitions of so it is the degree of what we have on the nth step is equal to Pn. And the evident grading that the degree of I is equal I or minus I, it depends, and we have such grading 0, 1, 2, 3, 4, and so on. Okay, now I can formulate the problem. Problem is following: that inside universal enveloping of Virasoro algebra, we have rather simple quadratic elements, which the letters denoted by K2. This element is actually infinite sum, and it is the following. It is A1, A minus 1, plus A2, A minus 2, plus A3, A minus 3, and plus so on. And in principle, for symmetricity, we can add here L0 squared twice, or in principle, if we do not like, we can just say that K2 is the element of such kind. This is some quadratic element, it's inside universal enveloping algebra, and it is acting here. This K2 preserve grading, so it means because of this structure, first acting L1 up and then L minus 1 down, then L2 up, L minus 2 down, and so on. Through such operators is acting like this, and give us the and it is infinite, but actually it is really acting in this representation, because if you take, for example, subspace here, then you have L3, L minus 3 is acting, and L4 and L minus 4 is acting by 0 on this space. Therefore, we have a well-defined operator acting there. And so this operator is just finite matrix, and the problem is to find eigenvalues, eigenvectors, and so on. Well, and for the people, maybe later I explain how it related with KdV, and even I explain what is KdV matrix. But in principle, this problem is that KdV is some Hamiltonian system, and we have the simplest Hamiltonian there, and after quantization, it gives us some operator acting on some space, and this is just this, precisely this. Therefore, problem of diagonalization of this operator is important, and people tried for many years to do it, and what is possible to prove, no, surely with some efforts, but it may be also, it's much simpler. First of all, this K2 is a part of integrable system. Yes, and it means that we can construct a system of operators inside universal OpenCourseWare which commute with him. So, for example, K3 is some. No, I cannot write it precisely, and I do not want, but it takes structure alpha, beta, and gamma. Alpha beta plus gamma equals 0, plus some quadratic terms, and here we have to put normal ordering. It does not matter what does it mean, but it is some cubic expression inside universal algebra, and it commutes with K2, and we can construct more of them, K3, K4, and so on. And if we know this, we are living in some area of integrable system, and people should expect that standard machinery of integrable system can be applied here. And only now it is clear that it is possible. So, in the title of lecture is something about Bethe ansatz and so on. And really Bethe ansatz can be applied. And the reason why that this Vermar, no, I do not know how much I can explain about geometry, but geometry is behind this. You see that this is a Vermar representation, but that the size of this space is a number of partitions. So it means it's natural to expect that Hilbert's scheme is somewhere behind this. And it is really so. And well, so again, in the end of, probably near the end of my lecture, somewhere near the end, I explained what kind of this PDV system as a part of some big class of integrable systems, which appear in some geometry. And I explained how to diagonalize such system, how to write Bethe equations and who are Bethe equations. This all I explained well. And suppose this is my goal or my direction. Yes, and no, before start, let me just say a few words. Again, if in what I said, if there are sorry involved in this game, it means that conformal field theorem and things like this are somewhere not far from what I'm talking. And also some other things are involved. I said that geometry, like studying this instanton manifolds and things like that, are also there. And technically, what is using something not far from quantum group and some things around them, it is not necessary, at least in the first half of the lecture, to know something about quantum groups. I try to explain. But actually, what I start to explain in a few minutes is some part of some approach to quantum group business, and so it was. So I start with what is calling the shuffle algebras. And today, definitely, I will talk only about that. This is the shuffle algebra is just a construction more or less from elementary algebra, and this is what the simplest possible algebra which people know is the polynomial algebra in n variable, or infinitely many variable. Yes, and this is also the name of the algebra of polynomials. And the simplest possible deformation of polynomials in a class of associative graded algebra, what is calling this Q polynomials. And Q polynomials is a very similar object. This is the algebra generated. No, maybe let us call them by, no, maybe the same name, x1, and so on, xn. Yes, but in algebra of polynomials, xi at j equal to j xi, but now not. Now xi at j equal qij at j xi, and here, in the simplest approach, so qij plus some numbers, and to be more precise, it is qii have to be equal 1, first of all. Otherwise, it has no deep meaning. But let us suppose this. And also, qij times qji have to be equal 1. Now, after that, we have a definition of some algebra generated by access with such kind of relation, and name of this is Q polynomials. And this algebra depends in matrix Qij. No simple but interesting algebra. We discuss about such kind of algebras. No, not a lot, but at least something. Well, but I need this, no, how to say it. And here we have construction of this algebra of Q polynomial in terms of generators and relations. But now I want to present a little bit actually very similar construction, but in some sense more concrete or more precise. I don't know how to say it well. But this construction is going on by which way? Let us take, suppose S is a set. This set, for simplicity, in principle, it can be infinite, and it will be infinite. But now, suppose it is a finite set, just to compare with this. And suppose we have functions, lambda, from S times S, also two fields which we have, but in our case, for simplicity, let it be just a complex number. Yes, and after that, I can use this function lambda to construct the algebra. Well, elements. Now, this algebra will be, name of this algebra will be shuffled algebra connected with this function lambda, and about product. Well, about product and about the algebra. Algebra will be graded. No, that it will be algebra E, and it is A0 plus A1 plus A2 A0 graded algebra, A0 just complex number. It is graded, it means that the product is MF AI times Bj to AI plus J. Yes, and each AI is the maybe M beta space of symmetric functions S times S times S M time into C. So element of this AM is function in M variables from S, which I denote by small s. Symmetric function. Now about the product. So suppose I have such function f, say from AM and other j from AM, then the product is what? It is like this. And it has to depend in, because of grading, in n plus m s's, s1, s2, and so on, sn plus m. And it is given by a simple formula, and this formula is what? F, s1, s2, and so on, s. F depending in m times g s m plus 1 s m plus n. Then it is a product of our function lambda s alpha s beta. Alpha run from 1 to m, beta run from n plus 1 to n plus m, and here we have symmetrization. No, I need to get a symmetric function in S1 and so on Sm, and symmetrization is through this, just symmetrize S1, S2, and Sm plus 1 and Sm plus 1. The name shuffle is because of this card terminology, because it means how this symmetrization is going on. Because they are symmetric in S, this group of S and this group for S. If we make symmetrization, I have to put S's, this group of S's in some places between these S's. So the same what I am doing when I arrange a bunch of cards. So anyway, this is a product, and this product, no, it is symmetrization and so on, but if you look to this formula, it is completely evident that this product has the structure of associative algebra on this state. So as a result, I have some simple construction of associative algebra, and the question is in what the relation of this algebra with the algebra of skew polynomial. They are very close things. It's not precisely the same thing, but very close. To see if, let us suppose that function lambda from S times S to C is actually have not zeros for simplicity. That is, goes to C star. After that, let us use some notations. This notation can be what? That surely maybe some comment. So in general, function lambda can be just zero. in this case, no chance to get algebra of such kind, and the product will be just 0. But if lambda is not such kind, for example, this one, then what? Then I can take A1 and suppose that, let us denote delta S is delta function. So A1 is what? A1 is function in S. And suppose that delta S is a function which is 1 in S and 0 in other points. And I can, without problem, calculate the product delta S1 times delta S2 in one order, and delta S2 and delta S1 in other order. And from the formula it is evident that the product in one order and product in other order is differ by constant. And this constant, this and difference of this and this is what? Is, I think, lambda S1 S2 divided to lambda S2 S1. So maybe open. Well, so that, again, such product will be function on S times S, which is non-trivial only on a pair S1, S2. And this is also. And because of this, the two products differ by such numbers, and this is the same as in algebra of skew polynomials. And it is a very, very simple exercise to see that if actually function is such type, then this algebra is generated by A1. So it means that at least in this case, this algebra is the algebra of skew polynomials. Yes, and it's okay. And not troubles, but it's a difference of this algebra of skew polynomials appear in the case when function lambda have zeros. Okay, so I have definition of shuffle algebra, and later we discuss a lot something about even in this simple case, but let me introduce now the algebra which I will work. And so first of all, such kind of algebra, I said that S is finite set, but for such definition it is surely not necessary. I can take SS infinite set and lambda every clear function, and I get some algebra. And but if S is infinite dimensional, that it is hard to say who will be generators and so on, at least in general. But construction with algebra I have. But let me introduce some of our examples which we will work with. So example. How this construction works. First of all, let S be infinite set, even more than that. Let S be C. Yes, and let us take function lambda in two variables, S1, S2, from C times C into numbers, into C, it will just function into variables, and I took C because I want to suppose something about this function, and first let lambda be polynomial. Polynomial will be too slow. Let lambda be some rational function. Yes, and the most popular example, which I write immediately, lambda S1, S2, it is no, S is not good to use if we are talking about just function. So suppose that lambda depending in Z. In Z1, Z2. Z is better notation for complex number. Anyway, the most popular choice of rational function is following. Let us take Z1 minus Q2 divided to Z1 minus Z2. Well, and let us have in mind for short period just this function. And now let us look how this product is working. But first of all, we can take as F and G polynomial, symmetric, in Z1 and so on. Now, well, and about the now about product, you see that we have F depending symmetric polynomial in M value, and product to F. I just write again the same formula: F times G depending in Z1 and so on, Z and plus M. And so the formula is just the same, and it is what? It is F symmetrization Z1 and so on Zm times G Zm plus 1 Zm plus n. Here I have a product of lambda Z alpha Z beta. Again, Z alpha from this group, Z beta from this group, and symmetrization is going on by this way. And again, let me write lambda is this. So this is a good product. So what we have to check something. So the result of product of two polynomials is also polynomial. But this is evident. This is evident because of what? That we take, so this is polynomial, but this is a rational function. This rational function has poles of the drag. But after that I make up symmetrization. But poles we have of order 1. But symmetric function in n variables cannot have pole of diagonal of order 1. It has poles of order 2, maybe 4, and so on. But 1 it is not possible. And so it means that this formula, we have many terms, and each term has poles on the diagonal. But after symmetrization, these poles cancel. So therefore, this is well define product on a space of symmetric polynomials, well, and let me formulate simple property of this algebra, and maybe because we need some exercises, then exercises about this algebra is good to formulate right now. And this will be what? First of all, what I want to say now that it is not exercises, but it is evidence statement, the evidence property. Suppose function lambda is equal 1. It means that parameter q, it happening if parameter q is there is 1. Then in this case, product is commutative. And algebra is generated by first component. And first component is function in one variable. And no, because we are talking about polynomials now, that first component is polynomial in one variable in Z. So well, if I want to formulate the exercise, maybe no, it's okay. Here it is. So now a product is commutative, and algebra is generated by polynomials in one variables, and in this case, when lambda is 1, this algebra is algebra of polynomials in infinite set of generators. And about these generators, well, we have them just in first grading. So generators are bases in this space, in 1, x, x squared, and so on. Yes, and yes, and surely for generic Q, we can understand this algebra as deformation of algebra in infinite set of generators. Fine. And second, let us consider the subalgebra of this shuffle algebra generated by first segment of this. I want to consider the subalgebra of this, what we have here, generated by elements 1, x, x squared, and so on, x, n minus 1. So, or just generated by a space of polynomials with degree restriction. The degree is less than 1. So, this algebra, which generated by n elements, let us denote this algebra by a, maybe b, n, And again, it may be simple exercise that it will be two exercises. One is simple, A, that for Q equal 1, B n is polynomial algebra. N generators. Exercise a little bit more complicated. Exercise B is suppose that Q is for any Q, suppose Q generic or some Q, that write the quadratic relations in my algebra Bn. Let me just understand what I want. Well, algebra B1 is just algebra generated by 1 from Cx, and this algebra is surely polynomial algebra in one variable. What is B2? If we are talking about B2, how to no, first of all, excuse me, I change the notation. Here was Z, here they become X. But anyway, I have in mind the same thing. Suppose just Z become X now. Anyway, I have in B2 I have 1 and X. And then I have to calculate the product in two directions. How to do it? That I have 1 and then I have X. And I want to calculate their product. Again, the definition of product, notation for product in such algebra always will be star, like this. So, what is this? So, if I calculate 1 times x, what is this? So, it will be function in two variables, because I change, unfortunately, notation. It will be function in variables x1 and x2. And what is this? It will be, it will be x2 times x1 minus q x2 to x1 minus x2. And here I have to symmetrize. So I have to add term where I write x1 and x2 in two opposite order. So it was what? x1 times x2 minus q x1 divided to x2 minus x1. And probably it is good to put 1/2 here. Or I calculate x. What will be the change? Change will be that here I will have now x1, and here I will have x2. And then I have to make symmetrization. Yes, and the problem is compare these two products in two different orders. Yes, and it will be, no, it is not big deal to do, and you will see that No, I cannot do it right now. Maybe I will do it a little bit later because of some reason. But you see, you get two symmetric polynomials and two variables. And actually one Q or Q inverse. Let me put plus minus 1 because I cannot be sure. Yes, and so it means that no, up to this algebra we generate by 1 and x is simple. It is polynomial for generic Q. This is polynomial algebra, which is just the algebra of Q polynomials, which such commutation relation. Yes, but if you take 1x and x squared, then what is the problem now? I want to say that this algebra is for this B3 is algebra with 3 generators. And we know, at least I claim, that this algebra for Q equal 1 is polynomial algebra in 3 generators. Now, if Q is, for generic Q, let us not talk just now, but if Q is not far from 1, the algebra is this algebra is generated by 3 generators and has some quadratic relation. And if we consider just polynomial algebra in 3 generators, then this algebra has 3 defining relations. It says that this commute with this commute with this, and this commute with this. After deformation, we have also algebra in 3 generators with 3 defining relations. And this is the problem which I have here in mind, just to write down explicitly these quadratic relations. If people never did it, that first do it for B3 and finish calculation for B2, and then to do it in general, and just write down it in some concise form. It's possible to write down them in rather good form. Okay. Now, let me discuss. No, we have definition now, and we discuss even one example. No, main definition that I can take arbitrary function and work out with symmetric function with some properties. And the question is what possibility in principle I have. Well, so now we have many possibilities how to describe this algebra, but again, next example is following. Let me take, suppose, function lambda in, let me return to z, z1 and z2 equal to okay, so excuse me, let me postpone a little bit. Examples will be, but next part of this shuffle algebra will relate. Relations, it is a problem, it's concerning the problem which appear for this shuffle algebras even in the simplest case. When S is finite set and lambda is some function, but now let us not suppose that in principle lambda, I admit lambda to have zeros. And well, now we have simple problem about shuffle algebra in this case. No, well, our shuffle algebra is A0 plus A1 plus A2 plus so on, and the question. No, the question is the following: when shuffle algebra is generated by A1. No, I said, and it's really evident, that if lambda have not zeros, then algebra generated by A1. And opposite example, when lambda is 0, is definitely not. And again, this question also can be a problem for students. But I want to discuss it, not to solve it completely, but well, I wanted to formulate the following thing. Well, suppose that lambda, no, I said lambda is just identically 0, then algebra definitely not generated by A1, and it means as algebra it has a lot of generators and so on. And but between lambda equals 0 and lambda which has not 0 at all, it is many intermediate situations. And to explain what is going on, let me formulate the simple proposition. Now, this proposition is following. But before proposition with definition, the set of elements S1, S2, S3, and so on, as R, form a wheel if the following condition is true. Lambda S1, S2 is 0, lambda S2, S3 is 0, lambda SR minus 1, R is 0, and also lambda SR S1 is 0. So what does it mean? It means that if I set of elements form a wheel, if I can draw a picture like this, S1, S2, S3, and so on, SR, the last one. And if lambda is 0 on this pair, on this pair, on this pair, on this pair, and so on, that we say that this set of elements S1, S2, S3, and SR form a wheel. Yes, and this is a definition of a wheel, and terminology, the function f from SSS, suppose L times to C, satisfy wheel condition if the following is true. F surely has to be symmetric function, and F S1 and so on S A is 0 if some subset elements from here satisfy wheel condition. So again, this is a part of this definition. Function f satisfies wheel condition if f is 0 on the following things. If on this subset, some S1, so we have subset here, S1, S2, S3, and so on, and some R, such that this set of S form a wheel. Now this is a definition, and now proposition. Proposition just say that suppose F satisfy wheel condition and G satisfy wheel condition. Then F G also satisfy wheel condition.
Do you fix size of wheel?
No.
Any wheel.
Any wheel. Yes, and no, I want to say that this is no again. Any wheel. So I take function and just check. I take any set of S which satisfies wheel condition and have to be 0 if a part of this S satisfies this wheel condition. So for any wheel, such function have to be 0. This is the definition, and now the proposition is this. Well, no, I want to say that it is almost evident. If you want to see it is enough to look to the formula for a product. That formula for the product, I recall you, that I have some F and some J, and then this S1 and so on, Sn. And what? It was symmetrization of F, S1, n plus n. Sm times G, S, n plus 1, and so n plus n. Yes, and here we have this product of lambda. That's alpha and that's b. Well, so what my proposition says, that suppose here I have this segment from S1 to SR, which is wheel, here. And then I want to see that, I argue that in this case, this formula is also 0 of this if F and J are satisfied wheel condition. Well, so, but it is, when I calculate it, it is a formula for symmetrization. And let us look to each term in this symmetrization. And for example, this one. So this wheel can be here or here. In this case, okay, because they both satisfy wheel condition. But this set of S, excuse me, that again, it is like if I take just S1 SR, this element is here, and so it is 0. So it's okay. Or in principle, it can be bigger than this. In principle, part is here, part is here. But in general, what is happening? If you have such part here and you have some term of this formula, some S are here, some S are here. Yes, and then, it can be easy to see that zeros are from this, appear from wheel condition, because we have many lambdas here. And if you look carefully to this formula, you see it, and we will check it. I explained to you the simple example where it is working, you will see. But here was the problem. When trouble algebra is generated by A1, and surely my proposition says that it is not so if we have non-trivial wheel. Now, in this case, the part which is generated by A1 give you only function which satisfy wheel condition. So it means that if we have non-trivial wheels, there's no way to get all algebra from A1. No. no, about this problem that I like if people to try to understand. For example, suppose, to be honest, I do not remember the answer to this problem. So I will be happy if somebody solves it fully. It is not complicated, but nevertheless, or at least give some partial result. No, this is correct. After that, suppose that function lambda is such that no will condition. So lambda has zeros somewhere, but we cannot organize will from the point such that this will condition is true. Is it true that in this case the algebra is generated by A1, or it is some counterexample? I will be happy in both cases. Anyway, now let me no, from this it is not, maybe it is not so easy to see immediately that this is correct. But let us consider our main example. I mean that now suppose that S is infinite and even C, and suppose this was algebra with function, what was there is Z1 minus QZ2 over Z1 minus Z2 and I product of the polynomials. But so will condition, for will condition, it is not so important. I play with polynomials and with other functions, it is not so important. But about the question about will, it is easy. So now this function lambda Z1, Z2, it even has poles, but we do not afraid poles. Then I explain, but it has zeros here. Zeros is more important for my will condition, and will appear so well when now S becomes Z, and will, this is in a case if I can draw it by this way, Z1, Z2, Z3, and so on, and here it has to be zero on this function. It means that the ratio of them has to be equal Q. Therefore, non-trivial will condition appear only in a case when Q is root of unity. Q some power n equal 1. In this case, we have will conditions, and therefore what? What I'm talking now. So suppose that Q is a root of unity of order n, and suppose that Q is primitive root of unity. Now, what is going on? That first place where this root will condition is working, the function in n variable, Z1 and so on, Zn. And my condition now is the following, that if, for example, if I take a product, so such set of functions is a part of an. This is n grading space in my algebra. And suppose I have a product, an times a1, an minus 1 times a1 to an. So what the formula is? So suppose g from here and some function in one variable, say h, suppose from here, then I have to write g, z1, and so on, zn minus 1 times h, zn times the product lambda, z alpha, zn, alpha run from 1 to n minus 1, and then make up symmetrization. It is the result of the product, and now if you look to this formula, it is easier, I think, than to look to the general formula. Then in this case, this product will be 0 when on a wheel. And this is because we have so many terms here. And so, you know, if you just take any term here and substitute z, q squared, and so on, then you get 0. More or less because of the evident reason, because one of the terms here becomes 0 in this case. So this is the way how it is working. Again, problem. No, even if you solve the problem for lambda and for when S is finite set and so on, from that, at least immediately what I want to say now is not following. The problem here is following. Suppose Q is not root of unity. Suppose for any n it is not root of unity, then algebra, shuffle algebra is generated by A1. Or it is more or less the same things, it is equivalent. A and B is the same. I repeat. Suppose Qn is 1 and Q is primitive root of unity, then algebra generated. Then subalgebra generated by A1 coincide with shuffle algebra till degree n minus 1. So it means that I have A1, then A1 times A1, and so on. And so this is A1, this product of A1 times A1, and it coincides with A2. Then A1 times A1 times A1, this coincides with A3, and so on until An minus 1, it will be like this. So A minus subspace generated by A minus 1 till this degree coincide with all symmetric functions. But trouble or happiness occur here in A1. Here I get not all functions, but only functions which are 0 on the diagonal, on this shifted diagonal, Z to Z and so on. Well, and no, I formulated them both because actually if you try to do this, what you actually will prove it is this. So. How many programs I have? 3 maybe, yes? Two or three? Maybe 2. No, maybe a little bit later I formulate one more. Okay. Let me return to examples. Well, what I can try. Now, first of all, so I want just to play a little bit with this definition of a shuffle, just trying polynomial and different functions to calculate the product. Well, so my starting point, as I said, was this function z1 minus q z2 over z1 minus z2. And by the way, such form of rational function, it is good because it is not necessary. In principle, we can work with this also. But homogeneous function is easier. But even here, well, what I can do. So here I have, when I use this function, I work with polynomials f g1, gn, times g, and so on, and calculate the product. I can change a little bit a definition and to get the same algebra. For example, suppose function lambda in C1 and C2 will just equal C1 minus UC2. And but definition of algebra, let us change a little bit. Well, now I take function f and g, and let me write down f, g, c1, so on, m plus m by the following way. So again, I write down f, c1, and so on, m times g, z m plus 1, and so on, z m plus m. Here, again, product lambda the alpha the beta, but here I put not symmetrization but alternation. And no, well, you see what we get as a result. Alternation, no, because of alternation, I get more or less the same algebra, because before I had this skew symmetric. See, now I have. But because of alternation, now algebra consists in skew symmetric function. But as algebra, it will be the same. No difference. So no, I just the question how much important this part. Not much. It's one. Then so because of this, now what we have, if we have function lambda of z1, z2, and I can construct either shuffle algebra using symmetrization or shuffle algebra using alternation. And in both cases, I get something. If you follow the list of examples, the next example should be when we have a product of 2 on the top, a product of 2 in the bottom. So I can take lambda z1, z2, z1, z1 minus z1, z2, z1 minus z2, z2, dy to z1 minus z2 squared. And now it will be more convenient because of a reason which will clear later. Let us consider algebra A0 plus A1 plus A2 plus so on, which each AI symmetric and symmetric function, and I want them to be Laurent polynomials. Laurent, no, in principle, I want them to be Laurent polynomials. Like in the case of 2. But it is not possible, because what? So, what I want to do? So, well, A0 is just C. A1 is suppose C unit. Yes, and if you calculate the product F, G, suppose they belong to A1. And I can calculate the product, F times G. So what it will be? It will be F, G1, G, G2, then we have this function lambda, C1, C2, and then symmetrization between one more term of such sort and one half. in front. Yes, but these functions are Laurent polynomials in a sense, but it has pool. And which pool depend in how we determine the algebra. So if determine it means what we use. So if we use alternation, then we get skew symmetric function as a result of alternation. But this skew symmetric function will have pool on the diagonal of degree 1. Because it's evident reason, it is skew symmetric functions. Because of this structure of Landau, we expect to have a polar order 2, but for skew symmetric function this is not possible. Therefore, we can have a sort of definition. I mean alternation version of sharp algebra for these functions. The element of this algebra are objects of the following type: P, V1, and so on, Vn. I, J. Here, product means product. I want to have skew symmetric function. It means that P symmetric Laurent polynomial. After that, on such set of functions, the product will be closed, and as a result, we get some associative algebra. It will be some construction. So again, alternation version is now closed. It means closed. But what we can say about wheel condition? For wheel condition, it is not important. Alternation we do or symmetrization because they are true in each term. But what wheel condition in this case? We can see, we can just repeat what I said before. And now, because of such structure of the function, wheel condition looks set of variables. Z1, ZR satisfy wheel condition. In this case, it is what? This is the same story, because Z is the same as S. They satisfy wheel conditions if we can write a wheel. In each side puts variable. If a ratio of Z1 and Z2 is one of these Q, and it can be Z1 over Z2, in this case can be either Q1 or Q2. Or here, ratio either Q1 or Q2. It means that set of the I now satisfies will condition if the I over the I plus 2, I think so it's correct, is either Q1 or Q2. Yes, and if so, our definition of will now is this, and function of such sort satisfy will condition if it is 0 in a case if some segment of the Z has such problem. Therefore, because of structure of real product, subspace of such functions which satisfy will condition gives us subalgebra. Yes, and this is the object which we study actually, and now, maybe main example. Suppose function lambda is Q1 minus Q1 2, Q1 minus Q2 Z2, Q1 minus Q3 Z2, divide to C1 minus 2Q. And now suppose for construction of the algebra in a product, we use sanitization. Then, in this case, the algebra still the sum of AM, and each AM is what? It is a symmetric polynomial in variables U1 and so on AM. Divide to the product the I minus the J squared. Where this guy is symmetric Laurent. Yes, and no, again, this is the same story. Function is a little bit different, but all is the same, and it's clear that a product AN times AM going to AN plus M. Main example, actually, main example, this is the case when Q1, Q2, Q3 is equal to 1. So this is main example, and in this case, no, what are will conditions? Will conditions are, no, it is the same story. It is sequence of Z1, Z2, Z3, and so on, and Zi over Zi plus 1 over Zi equal sum of Q, Q1, Q2, Q3, and algebra, this is functions which are zero on such diagonals of such conditions. And no, because Q1, Q2, Q3 is 1, then we have simple wheels. Z1, Z2, and Z3. If this ratio is Q1, this ratio is Q2, then this ratio is Q3. Therefore, we have wheel. Or we have wheel Z1, Z2, and Z3. Here we have Q1. Maybe here we have Q2. Here we have Q1, and here we have Q3. We have such special wheels. And in this case, it is possible to see that all other wheels just follow from that. Okay. I have some time, and the next part, which I started today, will be, I call it wheel conditions and set relation. Now, let me consider still the same example. So my function lambda Z1, Z2 will be Z1 minus Q1, Z2 with 3 factors. Now, let us look to my algebra. So I have A1 and I have A2. Now, set relation which I wrote starting some, no, in my case, Q1, Q2, Q3 is 1, and set relation appears here. But let us first discuss what is happening here. I have some associative algebra, and this associative algebra is generated by A1. And A1 are Laurent polynomials in Z and Z inverse. And what I have here is, as I said, Laurent polynomials in Z1 and Z2 divided by Z1 minus Z2 squared. So, what we can say about quadratic relation of this algebra, and also the size of this algebra. Well, first of all, let me say about this algebra some propositions. For this proposition, it will be easier to change the notation. So this EI, let me denote by EI, and this proposition is following, that in proposition that description of quadratic relations in the limit Q1, Q2, Q3 goes to 1. I maybe have some time to formulate it, but let me, before this, to formulate the following thing, that forget for a moment about all this business, and let us do the following. Let us consider the plane first, just C2 with the symplectic, with a coordinate, maybe P and Q, and symplectic form P. Well, and no, this symplectic form have a full, and so
You mean P minus Q?
no, PQ. So this is actually symplectic form on a product C star times C star. And if we have such symplectic form, we can determine the corresponding V algebra of Hamiltonian vector fields, or V algebra of Hamiltonians, better to say. On the space of functions here. Space of functions here are regular function are just C, P inverse, and so Q inverse. And using this Poisson form or corresponding Poisson structure, I can, this is the algebra of functions here. And what is this Lie algebra? Well, so we have yes. So the corresponding Poisson structure is, it has to be homogeneous. So corresponding Poisson structure is PQ d over dp over d over dq. And it means that if I calculate the bracket, then bracket of F and G is what? Is PQ dF over dP dJ over dQ means minus of dG over dP and dF over dQ. Well, maybe it is good to say why I switch the subject and explaining something about this. I want to say that this algebra, in some limit, when Q1, Q2, Q3 go to 1, and Q1, Q2, Q3 is 1, is very close to universal development of this Lie algebra. But I want to first explain something about this Lie algebra, and then connect it with what is going on here. Well, now let us look to this algebra. No, it is rather simple. And now if I take this formula and calculate the bracket, I, Qj, I prime, Qj prime, so it will be what? It will be P I plus I prime, Q J plus J prime, and here it will be what? It will be I J prime minus J I prime. This is correct? I think so. Now, let me, well, here we have a lattice like this. Now, so this is the origin. See, here this is the origin, yes, and it means that here we have 1, here I have Q, here I have Q squared, Q inverse, and so on. And here I have P, Q, and so on. So according to this formula, in this Lie algebra, this part is a commutative subalgebra, and this part is C Q Q inverse. This part is C Q Q inverse times P. Yes, and so this part is C Q Q inverse, and I have Q squared. Now, now about bracket. If I have Q I P bracket Q J P. Now, according to my formula, it will be what? will be Qi plus J P squared. No, it is just this with this, and so it is like. Now, first of all, it is not our business right now, but we have the same formula which I started with today. After sign, I had I as J equal J minus I and I plus J. Now, surely we have not the same here, but this coefficient we have there. Okay. Now, well, what I'm considering now, I have the algebra of vector field no, it is more or less as Hamiltonian vector fields on or algebra of Hamiltonians. Yes, and in this algebra, this is the algebra. No, first of all, this Lie algebra is very close to the algebra which we described by Cartan or Cartan-Serre type description. So, well, in this Lie algebra, we have big commutative subalgebra, which is this, which we can call Cartan subalgebra, if you like. We have subalgebra, which I want to call maximal nilpotent subalgebra, and it has which form? This is P times CP times C Q inverse. And we have also subalgebra which is opposite on this side. It is P inverse, C inverse, and here C Q inverse. So we see this Lie algebra, and now what I want to discuss now a little bit, that I take in this Lie algebra this maximal nilpotent subalgebra, and in this maximal nilpotent subalgebra, no, first of all, this decomposition is direct counterpart of what? If we have usual JLN, then we have diagonal matrices, which is maximal commutative subalgebra is this. We have upper triangular matrices, which is something like this, and lower triangular matrices, which is something like this. And now, what about relations? So, this subalgebra I denote it by n, maybe plus. This subalgebra I denote it by n minus. And equal P times Qi. No, I take these Hamiltonians here, and when I calculate the brackets, I get this, and so on. Yes, and first, element EI satisfies quadratic relation and such relations are following that no, because we had brackets there, I erased it, but it is EI, EJ, so this quadratic relation just means that the brackets EI and EJ equal I minus J times something. No, this quadratic relation means that I take, if I take EI and EJ, calculate the bracket, then it will be I minus J times element here, depending only in I plus J. Therefore, we have relation of such kind. Now now I want to say the following: the quadratic relations in this algebra, when so again, when Q1, Q2, Q3 are some numbers, and they Q1, Q2, Q3 go to 1, then quadratic relations in a limit, no, up to some constant, will give precisely what I'm saying there. In principle, I have to finish that few points here. I have there the algebra with the base I and J. And no bracket I defined, all other things here I defined, but let maybe next lecture I will start with this. Again, let me just explain what I said. Okay. I define shuffled algebra. I explain real condition. I'm saying that existence of real condition gives us a sort of relations. It means that, for example, what is happening? If I have algebra with real condition with Q1, Q2, Q3, and suppose this Q1, Q2, Q3 are generic, we have some algebra. If Q1, Q2, Q3 satisfy resonance condition, for example, Q1 times Q2 times 3 equals 1, then subalgebra which generated by first degree becomes small. Therefore, because because of wheel condition, we get some extra relation. And such kind of extra relations are, it is reasonable, and I explain later, to call them self-relations. So this is second thing, which I said. And next, I said the following. No, because we are interested in the case when Q1, Q2, Q3 product is equal 1, and we are interested in shuffled algebra with this Q1, Q2, Q3, then I did not explain it, but maybe it is good 2 minutes to again. So I wanted to say it, but it is possible now. Well, I have shuffled algebra with this function, z1 minus z1, 2, z1 minus z2, z2, z1 minus z3, z2, z1 minus z2. Yes, and then suppose that again that Q1 times Q2 times Q3 is 1, so we have to. So I consider algebra function P, Q1 and so on. Okay. Here I have product Zi minus matrix square with such wheel condition such that P satisfies wheel condition. And so we have some algebra with some product. And the fact which I want to try to explain, maybe it wasn't clear that I'm doing just this, that this algebra, if Q1, Q2, Q3 goes to 1, to generate two universal enveloping of this algebra, which I tried to start to explain. How to generate, we also discussed, because you see, in this algebra, it is interesting what is going on. That if naively set Q1, Q2, Q3 to 1, then corresponding algebra in the limit become commutative. But we can make limit more smart. If we do it more smart way, we can get this, or sometimes even more interesting things. Yes, but it is good just to have in mind what kind of object we have, because I do not know other way to explain, for example, the size of this algebra. But it is looking like universal enveloping of this part, and at least it gives us some image of what it is. So